Let's see if this works. Yeah, perfect. So our third talk is from Hassaan Inayatali, who's from University of Toronto, graduated this year. So big congrats to that. And now has been hired and working for Chicago Blackhawks from few weeks back, I assume. So please take it away.
As you mentioned, my name is Hassaan Inayatali. I just graduated from the University of Toronto. This project was done alongside my supervisor, my thesis supervisor from the University of Toronto, Professor Timothy Chan. It's titled Evaluating Space Creation in the National Hockey League Using Puck and Player Tracking Data. Players and coaches often refer to the value of creating space. Star ice hockey players are often described as having a magnetic pull with the ability to draw in defenders and create dangerous opportunities in the spaces left vacant by their opponents. There are two ways in which a player can create space, one of which is to create space for themselves, in which their movements allow themselves to be positioned in an area of higher value. Alternatively, they can create space for their teammates. This refers to movement which allows teammates to be positioned themselves in an area of higher value. For the purposes of this paper, we're focusing explicitly on puck space creation for teammates, so space creation for teammates while in possession of the puck. Past research on this topic that we draw inspiration from includes Spearman's Beyond Expected Goals paper written in 2018, as well as Born and Fernandez's Wide Open Spaces paper also written in 2018. These papers were from European football, but we found that a lot of the topics that we're going to be using are very applicable to ice hockey as well. So to kind of discuss the data that we're going to be using, you're going to be hearing from a talk from Miles and Tim's group next, and they use similar puck and player tracking data. This data comes from infrared emitters in the puck and the jerseys. Player data comes in at 12 hertz, puck data comes in at 60 hertz, and this data first became available during the 2019-2020 NHL playoffs. So in order to go about the process of quantifying space creation, we're going to break down our understanding of exactly what's going on in the ice into three components, and then we're going to build them back up into our understanding of space creation. So the first component we're going to examine is rink value, refers to the value of having possession in a given location on the ice. The second is rink control, the ability to control the puck at a given location on the ice. And then finally, transition probability, which refers to the probability the next on-puck event will occur at a given location. And I'm going to go a little bit more into detail into each of these components. Starting with rink value. So at a very basic level, we consider rink value to be the probability of scoring a goal from a given location. This was done by training a logistic regression model, expected goals model, using two features, distance and angle from the net. It's a very basic model to allow for the fact that at any location along the ice, we can immediately calculate what the probability of scoring is from that location. This uses 2015 play-by-play shot data from the NHL. Our next model is a rink control. Oh, sorry, one sec. The bottom plot there indicates our expected goals model going from left to right. So what you can see on the right, the area around the net is significantly redder, indicating a higher probability of scoring. This plot is scaled from 0 to 0.4, so being closer to the net indicates a higher probability of scoring. Our next model is our rink control model. So we use a bivariate normal distribution to model rink control. This allows us to incorporate a player's location, velocity, as well as distance from the puck. The reason it's important to incorporate each of these three features is that location allows you to incorporate where a player currently is. Velocity is highly relevant because the center of where your influence is isn't where you are, but rather where you are going. For example, if I'm traveling in this direction, it wouldn't make sense for my player influence to be here, but rather for it to be right in front of me. Additionally, distance from the puck allows you to incorporate the amount of time it would take for a player to be able to react to a particular puck going in your direction. For example, if I'm further away from the puck, I'll have a longer range of influence because I'll be able to make a play on the puck given that I have more time to reach it. So these three factors are each incorporated into the bivariate normal distribution, and it was first proposed by Born and Fernandez in 2018 in the Wide Open Spaces paper I mentioned earlier. So what you see there on the bottom left refers to the player influence. Let me see if I can get this. For this player here, what you can see here is that he's traveling in this particular direction, and his player influence is not centered at where he is, but rather in the direction that he's currently traveling, which is a really interesting application of this distribution. We can then aggregate the player influences of every player on the team to arrive at a team influence. And then finally, we take the logistic function and we subtract the team influence of one team from the other to arrive at a measure of rink control scaled between 0 and 1. So if we were to aggregate the player influences of each of the players in gray, and as well as each of the players in blue, and then take the logistic function, we move to our plot on the right, with blue representing higher areas of rink control for the blue team, and red indicating higher areas of control for the gray team. So that's our rink control model. Next, we have our transition probability model, which refers to the probability the next on-puck event will occur at a given location. So we have 4 steps to break down the process of calculating this probability. The first is getting a data set of intended passes. So examples where a pass was either successful or failed. We can then use the features that we have at the time a given pass was delivered to calculate the probability a given pass was successful. We then can take that model and apply it to any location. So given the state of the game at the time a pass was delivered, what's the probability that will be successful? And then finally, we normalize that such that the sum across the ice surface is equal to 1. This is going to be our final transition probability fabric. I'm going to go into each of these in more detail, so no need to think about it too much. So starting with intended passes. So we're not using event data for this, so we obtain intended passes through the following steps. Essentially, we identify successful passes. These are just simply transfers of possession between players on the same team. So from there, we're going to determine the distance between the passer and the receiver, as well as the pass duration. So let's say I pass the puck to Tim, who's right in front of me. We're going to look at the distance between me and Tim, as well as the time it took from the pass to get from me to Tim. So that's going to be for every single successful pass that we see in the data set, we're going to take these 2 pieces of information. We're then going to fit a linear regression on the distance and the time it took. So given how far I am from Tim, I can then predict how long I would expect a pass to take to get to Tim. Now what we can do is that we have a set of teammates. So now I have Tim, I have Miles, for example, I have a series of other people on my team. Given how far every player is away from me, I'm going to project the puck forward the second I don't have possession of the puck. So let's say I start with possession of the puck, and then all of a sudden the puck's away from me. I no longer am considered to have possession. If the pass was intended for Tim, if I project the puck forward, it's going to intersect with where Tim will be. But for example, if Miles was also on my team, it would go nowhere near him. So the idea being that essentially we project the puck forward based on how far each player is away from me. So given a series of players that are different distances, I'll project each of them forward. Whichever player is projected to be the closest to the puck at the time of their projected reception time, that's the player we consider to be the intended receiver. And then just as an additional note, we exclude dump-ins, shots, essentially examples of non-passing behavior, non-intended passing behavior. This brings us to our pass probability model. Now that we have a set of passes that we both know were successful or failed, we can fit a logistic regression model on this passing model, on these passes, based on 5 features. The first is the pass distance. So how long was the pass? The second is the distance between the receiver and puck at projected reception time. So this is what we were talking about earlier. If we project the puck forward and the player forward, and we know that a particular player is the intended receiver, how far are they apart at the time of the intended reception? So at the time we expect the receiver to receive the puck, how far is he from the puck? The defensive team influence at the origin. So we actually apply components of our player influence model within our pass probability model, in that we look at the defensive team influence, so the sum of all player influences on the defensive team, at the origin of the pass, at the midpoint of the pass, and the destination of the pass. And this brings us to our plot on the bottom left. So what we can see here is that the player here has possession of the puck. There's a high level of pass probability success to the corresponding defensive partner for the right defenseman here. However, there are also possible areas of pass receptions for each of these 2 players, as well as this player who's traveling in this particular direction. So this kind of shows how our pass probability model comes together using the components from where each player is going. As what you can also see is that the pass probability models are not centered at where the players are, but rather where they are going, indicating that we're capturing the right kind of effects that we'd like to be. We then take this model on the left and transition it to the transition probability on the model on the right by normalizing such that we divide each pass probability by the sum of all pass probabilities. The idea with this transition probability model essentially is that it's supposed to be intuitive. The probability that a pass will go to a particular location is proportional to the probability that a pass would be successful to that location. Now that we've broken down each of our three components, I'm going to talk about how we bring them together and get a measure of space creation, which is what we're trying to do in the first place. So moving from right to left, we start with this green box here on the right. So we're looking at the probability that the puck is transitioned to location R, an arbitrary location on the ice, given D, the instantaneous state of the game, as well as M, an instantaneous passing event. So for each of these terms, we assume that we're looking at the instantaneous state of the game, given the players around and every situation that's currently being examined. M refers to the fact that a pass was delivered at time D. So as I mentioned, P of TR given D comma M refers to the probability that the puck is transitioned to location R given the state of the game and an instantaneous passing event. So that's our transition probability model. Next, we have our rink control model, which is the probability that the puck would be controlled at location R given the puck was passed to that location. That's CR given TDM. And then finally, our rink value model is the probability of scoring given that the puck was able to be controlled at that location and transitioned given the state of the game, as I mentioned. So if you were to multiply each of these three terms together, what you're going to get is the probability of scoring, GR, given, like the probability of scoring at location R, given a puck was passed to a particular location, it was controlled at that location, and the instantaneous state of the game. So that's how we bring each of these three variables together. We'll have that at location R, and if we were to sum this across the entire rink surface, we get our combined model, which is the probability of scoring given the instantaneous state of the game and a passing event. And that's kind of our combined model, how we bring these three variables together. Just to visualize that more clearly, we can see each component of the model as well as the combined model in the bottom right. So starting on the top left, this is our rink value model. As we discussed earlier, it's the same plot as what I've been showing, as what I showed in the rink value section. We have our rink control model, very similar. What we see here is that the higher areas of rink control are for the players along the half boards and the players down low. And the player currently in possession of the puck is at the point. Our transition probability model shows where each player is, as well as where the possible passes could be going within the next at the current instantaneous state. So we see here that there's a high possibility of a pass being delivered to the player along the half boards, as well as over here. And then there are smaller areas of transition probability to the player that's in the slot, as well as the player down low. When we multiply these three factors together, we see that the highest probability of scoring given an instantaneous passing event would be to the player down low, given that what we saw here is that there's the probability that they'd be able to control it is quite possible. They're in an area of danger, and there's a possibility of receiving the pass at that location. So that's how we bring each of these three components together. So how can we use this in a more practical setting? The first is through tactical analysis. We can identify moments where players create space for their teammates. So when we go from the left to the right, we see how the probability of scoring has changed over the duration of the possession. So to start, this player has possession of the puck in their own zone, and the only possibility of scoring on the next on-puck event would be a pass here that would allow the teammate to break through and possibly score in that situation. By the end of the possession, the player has moved into the offensive zone. What we can see here is that the orders of magnitude has increased by 1. So we've gone from 10 to the -6 to 10 to the -5, and that there is a high probability of scoring in this region, given that this is a 2-on-1 and there's a passing lane to a dangerous area. And so we can kind of see how we've taken all these theoretical concepts and brought them into an understanding of the probability of scoring. Now going into like a larger player evaluation, we can now calculate the probability of scoring at any instantaneous moment given a player has possession of the puck. And what we want to do is aggregate this across all of the possessions for a particular player. We can then get an understanding of the on-puck space generation. That's the metric that we've developed throughout this paper, which allows us to understand how players are creating space throughout for their teammates. For time and computational constraints, we only ran this process for 35 NHL games, but we had 8 teams with 5 or more games to get a better understanding of, to get a larger sample of each player's results. This results in 74 forwards and 38 defensemen being analyzed. To start looking at the distributions of player results, One thing that we note is that the 80th percentile forward generates 3 times more on puck space generation per time on ice compared to defensemen. We can see here in the 80th percentile that forwards are generating roughly 3 times more than defensemen. A very similar trend holds through for goals per time on ice. Additionally, as you go wider in the distribution, the spreads get higher. So what we see here is that relative to the rest of the population, as we get higher in the distribution, the top end forwards create significantly more OPSG per time on ice relative to the top end defensemen. And this can also be seen in goals per time on ice. For assists per time on ice, we see a similar trend as OPSG, but generally we find that assists are more clustered together. The CDFs also get wider as we go higher in the distribution as well. So you can see similarly how assists have forwards generally create slightly lower amounts of assists relative to defensemen in terms of the CDF. So now looking at some higher level results, one thing that we notice is that forwards create approximately 3 times more OPSG per time on ice relative to defensemen. That can be seen here, 0.0048 compared to 0.0017. Between goals and assists, we find for forwards that the correlation between forwards and between OPSG per time on ice and assists per time on ice is the highest, 0.654. That can be seen here. We think that makes sense given that our metric is designed to measure how players are creating space, and generally players who create space are more likely to be generating assists for their teammates. For defensemen, we find that the correlation is higher between goals per time on ice compared to assists per time on ice. We posit that one possibility for why this might occur is that while defensemen are able to generate assists often from the point, from passing it along the half board, they're passing it down low. The ways in which players, defensemen specifically, will be able to create space is by driving the puck into more dangerous areas, and in doing so, possibly being able to generate goals for themselves. And that's one possibility for why we see the higher correlation for goals. One other additional thing to note is that generally the correlation for forwards is higher than defensemen across both categories. And the reason this might make sense, defensemen are last to join the rush. They play from the point. Generally, they're not creating nearly as much space relative to forwards. So it makes sense that given that forwards are constantly going around the zone to create opportunities for their teammates, that the correlations would be higher. One other component in the bottom that we see, we've broken it down by position. We see that centers and left wings generally create more space compared to right wings, and left defensemen more than right defensemen. Given that we're working with a smaller sample size, we would just be hesitant to draw very large conclusions from this. We'd like to expand our analysis to be more, to get a better understanding of this relationship. What we can also do is look at the team level. We can look at the correlation between OPSG differential on a game level basis, and then take that and compare it to shot attempts and shots on goal. So we see that there's a moderately positive correlation with shot attempts and shots on goal, 0.647 and 0.603, while we found a slightly negative correlation with goal differential. And this is something that might be subject to sample size. So we're going to take a look in trying to look at a broader set. But for the most part, these are the results we found at the team level. Just discussing some model limitations. The first is that the rink control is a descriptive model. It's not calibrated to event outcomes. So we would like to get a better understanding of whether or not we can calibrate our rink control model compared to a particular pass being received or a puck recovery in the future. For rink value, it assumes that a receiver can shoot. Shots and expected goals models are inherently selection biased in that players are able to shoot, and we know that they're able to shoot because they took a shot, whereas our model assumes that a player receiving the puck would automatically be able to shoot given that they controlled the puck from that location. The transition probability model does not account for offsides. So if a player was in a particular position where they couldn't receive the puck, but they were in a high danger area, that could possibly be a limiting factor in this model. And then finally, the combined model does not value passing lanes differently. We know inherently that seam passes and low to high passes create higher danger opportunities. But if a player creates space in a passing lane across the seam, it wouldn't be necessarily encapsulated as well as it should be, given that the player might not necessarily be in an area of higher value, even though the pass across would create a dangerous opportunity. To conclude, we've gone over 3 new frameworks: the pass probability fabric, the transition probability fabric, and our new model called on-puck space generation. Additional steps include completing this process across an entire season to get a better understanding of consistency, as well as getting a larger sample so that we can take a deeper look at some of our team level correlations. understand whether or not how repeatable this particular skill is across multiple seasons. One other component is getting a better understanding of off-puck space creation. Some of the work that we're using from, for example, the Beyond Expected Goals from William Spearman, that comes from European football, and a lot of that focuses on off-ball space creation. We find that it would be very important to try to measure that in hockey as well, and this framework could allow that in the future. And then finally, we've taken a look at pass probability fabrics, and getting a better understanding of how well teams are blocking passes relative to expectation is a further step that we could take. And yeah, thank you very much.
Questions from the audience? So, yeah.
Yeah, great talk. So one thing I was thinking about is that, for example, so it's modeling, all players on the ice and your expected chance that they're going to receive the puck. Something that affects that is a player's speed. If I'm passing to Matthews versus Ryan Reeves, Matthews might get to the puck more than Reeves. So that's one example of something that could be incorporated. Do you think that would have a big effect? And what other things would you like to incorporate?
I think so. We encapsulate the player's speed at the time that the pass was delivered. So, for example, you're talking about Austin Matthews versus Ryan Reeves. If Austin Matthews is going at a considerably higher speed at the time the pass was delivered, we're going to project the player forward along with the puck forward based on their speed at the time that the pass was delivered. So we do encapsulate the speed of a player at the time the pass is delivered, if that makes sense.
Yeah, it does. I was also thinking maybe a player's reach, for example, like, taller players, but I just, there might be player specific attributes that could improve the model.
Yeah, no, for sure. If you try to encapsulate like stick length and that kind of thing, you could maybe potentially get, we think that it's fairly negligible if you were to be able to encapsulate like slightly more reach, but if you were to try to build that into the model, it could definitely improve it for sure. Yep.
So I think the focus here was mostly on like passing probabilities. Have you looked into shooting probabilities as well? Like, for example, if you have Nikita Kucherov on the half wall, he's a threat to shoot and also a threat to pass. Whereas if you look at like Mitch Marner on the half wall, he's less of a threat to shoot. So do you think that affects the spacing creation as well?
I think the idea is that we're focused specifically on given a next on puck event, what's the probability that they'll score from that location? So we're focusing specifically on we're not necessarily focusing on whether or not they have the option to pass or not. We're focusing explicitly on if they were to shoot from that location, what would the probability of them scoring be from that particular location? So there might be, one thing that was a limitation is that, like I mentioned with the rink value model, we assume the receiver of the pass will shoot. But if we were to be more, if we were to improve this model, one thing that we could very much do is encapsulate the expected outcome of all possible decisions a player could make. So the probability of them passing given the particular circumstances around them and being better suited to encapsulate that kind of information. Tim?
Can I see slide 24? When you talk about the different positions,
yes,
those are averages, I'm assuming, in the last table.
Yep.
And so you said that there's a difference there, but did you check to see if they're statistically significant?
I did not check if they're statistically.
So there may not be any differences.
No, no. Yep.
Yeah, so I have a theory on that. It's mostly anecdotal. So at least from my sport, floorball, it's pretty clear that players shooting right-handed are better shooters just because they had a strong hand on the button. So maybe there's something to it that right-handed forwards and defenders are more shooters and left-handed are more passers and playmakers. So that would be my theory maybe on that.
Yeah, like Tim mentioned, we just within the amount of sample, we're not sure if these are statistically significant. Although if, let's say, this were to hold true at a larger scale, there's definitely some positional and role biases that we want to be able to encapsulate better. For example, left wingers have different roles within the same team. And for example, we're looking at only 8 teams. So if, let's say, the left wingers on this particular subset of teams are more likely to be driving play along the wing, whereas right defensemen are more likely to be playing in a more defensively oriented role, then you could get those results as well. And you would just want to be more mindful of how exactly the player came into contact with the puck and what situations they started with the puck.
I think it's related just to a technical thing that when you have your strong hand low, it enables you to shoot better. That's just my theory anyway. So something to look into for sure.
Yeah. Yep.
So thanks. I think it's nice that have these ideas from football, like passing models and pitch control, and so translate into hockey in a way that makes sense. But there is a difference between football and hockey, and that's that we have a board around the rink. So how do you deal with passes via the board?
So for the purposes of like the transition probability model, we do not look at like, at least in our like intended passes section here, one of the things that we excluded was any bank passes or rim passes because we just like they're very difficult to encapsulate with like the current methodology. Definitely something to look into for the future. In terms of like passes being accessible, Dave, as part of Tim's group, has looked into like passing lanes along the boards and that kind of thing. And I think it would definitely be relevant to encapsulate that kind of information when building a pass probability model, because you could get a better understanding of how exactly a player could reach a particular one of their teammates using the boards, for sure. No, that's a great point.
And any other, yeah, up there.
First of all, insane job. I think that took a while. What was the reason for doing that? What was your reason
The reason for combining?
for doing that work?
For doing this work. I had previously done some NFL related research involving like pressure and trying to better understand how players influence the quarterback in this particular area. And a lot of that work was derived originally from the wide open spaces paper that I referenced from Born and Fernandez. And I just thought that in general, hockey is very well suited to this kind of analysis, and it just hadn't really been done. But yeah, that's the main reason why.
Any other question? So I think I follow up with I mean, you have a lot of conditional probabilities in your saying. And we've heard some questions related to condition on certain players.
Yeah.
In terms of teams, like if we take Florida Panthers, so you see more dump-ins, for example. So now you exclude the dump-ins. Do you think your model would still work for them, or how would you incorporate dump-ins, for example?
Well, I think that generally we're focused on like specifically while players are in possession of the puck. And for example, Florida, you mentioned their dump-ins, but their dump-ins are designed to create like offensive zone opportunities where they'll be able to create space within the offensive zone and create those kinds of dangerous opportunities. So given that they're getting that larger amounts of possession and are able to generate dangerous opportunities, they're still going to show up very well in this model. It's just in the neutral zone, how they go about gaining that level of attack and creating that dangerous space is different from potentially the way other teams would go about creating that process. That makes sense?
Yeah, no, that makes sense. And I mean, another question that you probably can't answer now, but I think is interesting is sort of just understanding how many samples you need.
Oh yeah.
So I mean, as you go further, because like it seems like you can do pretty interesting stuff with few samples.
Sure.
So that means you can use it at sort of scouting at much finer granularity than if you need 2 seasons, etc.
For sure. No, you can definitely build this out with like a larger amount of data. And one of the things is that the possession model is rule-based, like we define it based on a particular set of characteristics. But if you were to incorporate event data, you'd have a better understanding of like, this is when a player came into possession of the puck. This is when a player lost possession of the puck. You don't need to do it's not nearly as computationally intensive as if you were going to do it the way we had to do it, which is like look at every single millisecond and get a better understanding of like who has possession of the puck. Things that are simple as that make things a lot easier for sure.
Okay, thank you. So let's thank the speakers.